Okay, so today we have 6.8, which is going to be about exponential growth and decay models. So we are going to be working with exponential functions that represents growth or decay. All right. So many natural phenomena have been found to follow the law that an amount A varies with time t according to the function A of t equals A initial times e to the kt, where A is your final amount, A initial is your initial or original amount, T is time, and K is your growth or decay constant. If K is greater than 0, then we have a growth problem. If K is less than 0, then we'll have a decay problem. So if K is positive, we're increasing. If K is negative, we're decreasing. And that's what's stated below. When amount A varies over time according to the equation, it is said to follow the exponential law or the law of uninhibited growth. Growth is greater than 0, decay is less than 0. Okay. The law of uninhibited growth accurately models the early stages of the cell division process. All right. So this is the formula we'll be using for growth. So let me get that off the screen. Get out of there. There we go. Okay. A model that gives a number n of cells in a culture after time t has passed is given by n of t equals n initial times e to the kt, where it's just like the equation above, except now we have the variable n. So n is the final amount of cells in a culture, t is time, n initial is the initial or beginning amount, and k is going to be positive because here we're going to talk about growth. So this is the formula we're going to use for the first two examples. Okay. So here we go. Bacterial growth. The pizza you ordered last night happened to be left out on the kitchen counter. We've all done that before. A colony of bacteria interested in your pizza decides to have a slice too. You decide to have a slice in the morning, but your scientist roommate states, according to the law of uninhibited growth, the bacteria's colony size on your pizza is now modeled by n of t equals 100 times e to the 0.045 t, where n is measured in grams and t is measured in days. And you tell your scientist roommate, it's too early for stuff like this. Okay. So, A, given the function above, determine the initial amount of bacteria. So remember that this is modeled after, let me draw a proper n. After n of t equals n initial times e to the kt. So n initial, the initial amount of bacteria, is going to be given by 100. You can also find that by plugging 0 in for t. So for A, the initial amount of bacteria is 100, and I think we are in grams. 100 grams. Okay. And then B, what is the growth rate of the bacteria? So now growth rate is given by K. K represents our growth. So for B, K is 0.045, which we can also turn into a percentage, saying that this bacteria on the pizza is growing at a rate of 4.5%. Okay. All right. And then C, what is the population after leaving the pizza out for 5 days? So all we're going to do here is plug in 5 for T. Move this over. There we go. Where am I? Right there. Okay. So for C, we're going to say N of 5 is equal to 100 times E to the 0.045 times 5. So we're just plugging in 5 for T. All right. And then I need a calculator. So Desmos, here we come. Do I have Desmos open? Probably not. Broken. Hide this. Perfect. There we go. I just need, no, I'll keep the graphic calculator. Sure. All right. And I'm going to type it in just like I see it. So 100 E raised to the 0.045 times 5. And after 5 days of leaving this pizza out on the counter, you see that the bacteria has grown to a size of 125.23 grams. I don't know who will leave pizza on the counter for 5 days, but don't do it. Okay. And then it says, D, how long will it take for the population to reach 140 grams? So this says how long. So this means we are looking for time. They're giving us the final amount. They're giving us that the bacteria has reached 140 grams. So this means that for D, we're going to take 140 and set it equal to our equation of 100 times E to the 0.045 T. So it says how long, so this means we have to look for time. Okay. And then let's go ahead and solve this. So the first thing we're going to do is divide by 100. And then I should get 1.4 equal to E to the 0.045 T. Okay. And then what we're going to do is convert from log to exponential. I'm sorry, from exponential to log. So when we do that, remember that the base of the exponential function becomes the base of the logarithm. So this is going to become natural log base E of the outside number of 1.4 set equal to the exponent of 0.045 T. So we have just converted from exponential to log. And the reason we use natural log is because the base of the natural log is E, which means we don't need to write that in there anymore. So now I just have natural log of 1.4 equal to 0.045 T. Now all we have to do to solve for T is divide by 0.045. 0.045. And here we get the natural log of 1.4 over 0.045. And we get that the bacteria's population will reach 140 grams when we hit 7.47 days. But of course, we can round and we can just say 7.5 days. Okay. And then if my math lab's really picky, it might make you just put 8 days, but hopefully they do 7.5. Okay, that's D. And then the last one, E, what is the doubling time for the population? Which means, once again, we are looking for time. So we want the population to double. So if the initial population is 100, this means if it doubles, it's going to be at 200. So once again, they're giving us the final amount. So this means that for E, we're going to take 200 and set it equal to our equation, e to the 0.045t. And all we have to do again, like the last one, is solve for t. Okay. So divide by 100, of course. And we'll get 2 equal to e to the 0.045t. And then once again, convert from exponential to logarithm. So it's going to be base e. So you will get the natural log base e of 2 set equal to the exponent, once again, 0.045t. We don't need that base of e in there, so we'll get natural log 2 equal to 0.045t. Divide by 0.045, 0.045, and calculator time. All right, let's see. Functions natural log 2 over 0.045. And we get that the population will double in 15.4 days. This means that you have left your pizza on the counter for 15 days. Eesh. Or maybe we threw it in the trash can, and this is what happens after 15 days. But this is how you model exponential growth. So, any questions on that? Stop popping up keyboard. Okay. And what's cool about this equation is that it's actually a graph as well. It has a graph and it shows how the bacteria is growing. So if I scroll down here, this is the exponential growth that we just found out from that given function. So as time goes on, we see that our bacteria is slowly growing day by day. And here's all the answers we found. After 5 days, we had 125 grams. After 7.5 days, we had 140 grams. And then after 15.4 days, we had 200 grams. I could even model this in Desmos and type that same function, e to the 0.045, but I have to use x. And there we go. And look at that. So same thing here. So initial population is 100. That's where we start. And then as time goes on, we see how the population of the bacteria is growing. Okay. That is until you finally decide to throw it away. Okay. So that is exponential growth. Is everybody good with that problem? Give me a thumbs up. Show me you're alive. There we go. Okay. Let's do it again. All right. Bacterial growth. A colony of bacteria growing in the community pool is increasing according to the law of uninhibited growth. A, if N is the number of cells and T is the time in hours, express N as a function of T. So what step A says is just find an equation that will model the growth of this bacteria. So it just wants the equation that can model this growth, a basic equation. And we know that equation already. It is the equation for growth. So for A, it's going to be N of T equals N initial times E to the KT. Okay. So there's A. We know that this equation, this formula, whatever you want to call it, models exponential growth. Okay. So B, if the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the pool. Okay. So here they're telling us, so for B, they're saying that the initial population will double in 3 hours. So what they're giving us is that N of 3, so after 3 hours, they're telling us that the population, the initial population, will double. So they're giving us that N of 3 equals 2 times the initial population. Okay. And then it says find the function that gives the number of cells in the pool. So what this is saying is solve for K. If we know the value of K, then we'll know the function that will give the accurate number of cells in the pool. So that's what this one is saying. It says solve for K. Okay, so what we're gonna do is take 2 initial and replace N of T. If we do that, we will be able to solve for K. So this means that we'll get 2 times N initial equal to N initial times E to the KT. Oh, sorry. Oh, not yet. One tiny mistake. We'll start over. We're still going to do that, but we're going to start with N of 3 and plug in 3 for T. There we go. Now this will make more sense. And now we know that N of 3 is 2 initial. So we'll have 2 initial, N initial, equal to N initial times E to the 3K. There we go. That's better. And then just solve for K. So what we're going to do here is divide by N initial. Your N initials will cancel, and you'll get 2 equals E to the 3K. Now just convert from exponential to log. And we get that here's the base. So it's E, which means we're going to use the natural log. So we've been doing this enough already. So we're just going to go to the next step and say the natural log of 2 is equal to the exponent of 3K. So natural log of 2 is equal to 3K. Now divide by 3. And let's see what the value of K is. Natural log of 2 over 3 And we get that K is equal to, and we'll do this at 3 decimal places, 0.231. Here's the value of K. But this equation is almost done because it says, I mean, this problem's almost done because it says, find the function that gives the number of cells in the pool. So the last piece of this is to create the function n of t equal to n initial times e to the 0.231 t. There we go. There's our function. Okay. All right. Wrote that really big. So let's see. Get some room. Okay, perfect. Okay, C. How long will it take for the size of the colony to triple? So for C, we are looking for time because it says how long. So for C, we want to know how long will it take for the size of the colony to triple. So the clue they're giving us is that after T hours, the original amount will triple. And now all we have to do is take 3 n initial and replace n of t with that. So we will get 3 times n initial equal to n initial times e to the 0.231 t. And now everything's set up, so we will just solve for t. Let me zoom in here. All right. We know we'll divide by n initial, and they'll cancel out. So we can move on to the next step and get 3 equal to e to the 0.231 t, and then convert from exponential to logarithm. And we will get the natural log of 3 equal to 0.231 t. And then divide by 0.231. All right, so calculate the natural log of 3 over 0.231. And t equals, we can do it to 4.8 hours. So the bacteria in the pool will triple in 4.8 hours. Okay. There's A, there's B, there's C, and then D says, how long will it take for the population to double a second time? So how long will it take for the population to quadruple? All right. Well, this one is a give me. All right. How long did it take for the population to double? Anybody? Anybody?
Sorry, I'm here. I'm trying to look, find it.
Read B.
Read B.
Read B.
Read B. Sorry. Yeah. So 0.231 or N of E to the.
No. Read problem B. How long does it take for the population, for the bacteria to double? Like, don't read our process, just
3 hours.
3 hours. So how long will it take for it to quadruple?
6.
There you go. Done.
Sorry.
There you go. And yes, we could set that up the other way as well. You could make it for n initial equal to n initial times e to the 0.231 t. And when you solve for t, you'll get 6 hours. But hey, why not read context clues, right? All right. Cool. All right, that is uninhibited growth. Is everybody good with that example? Got some thumbs. All right. All right, got some thumbs. Thanks. Okay, so those were growth. And now we have decay, which is the same exact equation, except different terms. This is going to be A of t equals A initial times e to the k t, but this time K is less than 0. So K is negative, meaning we are decaying. And of course, A is the final amount, T is in time, A initial is the original amount, and K is negative because it's going to represent decay. Okay, so all radioactive substances have a specific half-life, which is the time required for half of the radioactive substance to decay. In carbon dating, we use the fact that all living organisms contain 2 kinds of carbon, carbon 12 and 14. While an organism is living, the ratio of carbon 12 to carbon 14 is constant, but when an organism dies, the original amount of carbon 12 present remains unchanged, whereas the amount of carbon 14 begins to decrease. The change in carbon 14 to carbon 12 makes it possible to calculate when organisms died. Okay. All right. So let's go ahead and check out decay. All right. So traces of burned wood along with ancient stone tools used to hunt flying pigs, maybe they existed, maybe they didn't, were found in an archaeological dig in Chile contained approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,600 years, approximately when was the tree cut and burned? All right, cool. So we get to find out how old something is. But let's go ahead and list some of the clues they're giving us. Okay, so the first clue, we'll say clue 1. It says that the tools they found contained approximately 1.67% of the original amount of carbon-14. So this means that after some time t, there was 0.0167 of the original amount left, of the initial amount left of carbon-14. And then clue 2 says that the half-life of carbon-14 is 5,600 years. So this means that after 5,600 years, there was half of the original amount left of carbon-14. Okay, so we are going to use these clues to find out how old these ancient tools are. Okay, so this means that we are using, of course, this formula. A of t equals A initial times e to the kt. And the first thing we need to do is solve for K. And that's gonna be a common theme in most of these problems. You're gonna have to find K first based on the clues given. So we are gonna use clue number 2 to help us find K, because in clue number 2, they're giving us an actual unit of time. They're giving us 5,600 years. So we'll say find K, which means we'll take A of 5,600 and plug 5,600 in for time. And now we know that A of 5,600 is equal to 0.5 A initial. So that is going to replace A of 5,600. So this means that this becomes 0.5 A initial equal to A initial times E to the 5,600K. And again, you'll divide by A initial, they'll cancel out, and we will be left with 0.5 equals E to the 5,600K. And then we will convert from exponential to logarithm. And again, the natural log. We will have the natural log of 0.5 equal to 5,600K. And then divide by 5,600. And let's see what we get. Natural log of 0.5 over 5,600. And oh man, look at those decimal numbers. Let's go ahead and say negative 0.0000124. That's going to be our K. So we have found K, which means we can complete the actual equation for this problem, which will become A of t equals A initial times E to the negative 0.000124 t. And that means we're almost there. Again, let me make some room. There we go. Okay. Move. Okay, cool. Okay, so now let's go ahead and use clue number 1 to help find how old these ancient tools are. Okay, so clue 1 says that after some amount of time, there was 1.67% of the original amount left. So we are going to use that. So let me go ahead and see. And let's find time. So we know that A of t is equal to 0.0167 A initial. And we will now take that and set it equal to our new equation, A initial times E to the negative 0.00124 t. And now, just like we've been doing, let's go ahead and solve for t. You'll divide by A initial, which will leave us with 0.0167 equal to e to the negative 0.000124 t. Convert from exponential to log, and we'll have the natural log of 0.0167 equal to negative 0.000124 t, and then divide by negative 0.00124. And let's go ahead and type it in. Zero 0.0167 over negative 0.0012. Oh, did I miss a 0? 124. Okay. This means that these tools are going to be 33,003 years old. That's when flying pigs existed, guys. All right. So we see some of these processes are repetitive. You just have to get that setup down. So is everybody good on this one? No thumbs? No thumbs this time? All right, one thumb. All right. Can't wait for my future students to watch these and they'll be like, man, your students never talk to you. I'm like, I know. Okay, so that was growth and decay, and here is another model of decay. So this is called Newton's law of cooling. So Newton's law of cooling states that the temperature of a heated object decreases exponentially over time toward the temperature of the surrounding medium. The temperature U of a heated object at a given time t can be modeled by the following function. U of t equal to capital T plus U initial minus capital T times e to the kt, where k is less than 0. And the reason k is negative is because the heated object is now decreasing towards a surrounding medium temperature. Okay, so U of t will be the final temperature. T is, of course, in time. Capital T is your constant temperature of the surrounding medium, basically room temperature. U initial is the initial heat of the object, and K is your negative constant. All right. Okay. You're quite learners or quiet learners? You're quite the learners, right? Okay.
Why not both?
All right. So your favorite college meal, maybe still your favorite meal, ramen, is heated to 100 degrees Celsius. I think you just torch it, right? And is then allowed to cool in a room whose air temperature is 30 degrees Celsius. All right. So, A, if the temperature of the ramen is 80 degrees after 5 minutes, when will its temperature be 50 degrees Celsius? Okay, so let's put together some of the clues we're given here. Okay, there. Okay, so for A, we are given that the temperature of the ramen is 80 degrees after 5 minutes. So this means that U of 5 is equal to 80 degrees Celsius. There's one clue. And then we want to know, when will its temperature be 50 degrees Celsius? So this says, when will the temperature be 50 degrees Celsius? So there's some clues given. Okay, and now we want to fill out this equation from what we know. So our equation is U of t is equal to the room temperature. So it says that the ramen is allowed to cool in a room whose air temperature is 30 degrees. So remember that T, here I'll just rewrite the formula. T plus U initial minus T times E to the K T. Okay. So here capital T is the room temperature. So that's going to be 30 plus the initial temperature of the ramen, which is 100, minus the room temperature, times E to the KT. So here's the formula we're going to use. U of t equals 30 plus 70 E to the KT. Okay. And now we're going to use our clues. We know that after 5 minutes, the ramen is at 80 degrees Celsius. So that's what we're going to do here. So clue blue, the blue one, we're going to say U of 5 is going to be equal to 30 plus 70 E to the K times 5. But we know that U of 5 is 80 degrees Celsius. So we will substitute that in. So here we get 80 equal to 30 plus 70 E to the 5K. And now we solve for K like we've been doing. All right. Move that 30 over. We get 50 equals 70 times E to the 5K. Divide by 70. And we will get 5 over 7 equals E to the 5K. And then convert from exponential to log. Natural log again. Natural log of 5/7 is equal to 5K. Divide by 5. And natural log of 5/7 over 5 is equal to K. All right. Computer. Natural log of 5/7. Oops. Over 5. And let's have negative 0.067 equal to K. Which means we can fill out our equation, which happens to be now U of t equals 30 plus 70 E to the negative 0.067 T. Okay. And now, using this, we can find out the last part of A. The last part of A says, when will its temperature be 50 degrees? Let me box this. When will the temperature be 50 degrees? So that's U of T. Okay, so let's go ahead and use that. So we have U of T. Actually, I don't even need to write U of T. We're just going to write 50 is equal to 30 plus 70e to the negative 0.067 t. There we go. And let's solve for time. Move that 30 over. 20 equals 70. E to the negative 0.067 t. Divide by 70. You'll get 2 over 7 equals e to the negative 0.067 t. Convert to natural log. And you have natural log 2/7 equals negative 0.067 t. Divide by that, natural log of 2/7 over negative 0.067 equal to t, and calculate. 2 over 7 over negative 0.067. And time, the time it will take for the ramen to get to 50 degrees Celsius is going to be 18.7 minutes. There we go. Okay, that was all for A. Which means B. Determine the elapsed time before the temperature of the ramen is 35 degrees. So this means that for B, we are looking for, again, time. So for B, all we have to do is take 35 and set it equal to our equation below. 35 equals 30 plus 70 times e to the negative 0.067 t. And solve for time. Move that 30 over. 5 equals 70. E to the negative 0.067 t. Divide by 70 and you'll get 1. Oh, we can leave it as 5 over 70. Sure. 5 over 70 equals e to the negative 0.067 t. And then convert. And we'll have natural log of 570 equal to negative 0.067 t. Divide by negative 0.067. And let's see. And we get that we'll hit 35 degrees Celsius in 39.4 minutes. There we go. Okay, cool. Last one to answer. What do you notice about the temperature as time passes? Well, this goes for anything sitting at room temperature. As time passes, what temperature will the ramen finally be at? What's our room temperature?
Room temperature is 30.
That's it. So as time goes on, it can't get lower than 30, right?
No.
There you go. So for C, we'll say U of T will be 30 degrees Celsius. There we go. So as time passes, we see that the ramen is cooling and cooling to the room temperature of 30 degrees. All right, cool. So that was Newton's law of cooling. Is everybody good with that one?
Steps are a little bit long, but doable.
They're repetitive. I mean, the whole thing here is that it's just repetition. We've been solving for K, we're converting from exponential to log, so nothing new here, right? It's everything we've been doing up to this point, except word problems now, right? Okay, cool. Let's see a check mark and a thumb. Perfect. All right. Oh yeah, and there you go. Another graph to represent Newton's law of cooling. So we nuked our ramen to that 100 degrees Celsius. And then as time passes, we see that the temperature is decreasing and decreasing, and will finally level out at 30 degrees. Okay. All right, last one, logistic models. The exponential growth model, well, I should say N of T, but we know they're the same. As long as K is greater than 0, it's a growth model. This assumes uninhibited growth, meaning that the value of the function grows without limit. The logistic model can describe situations where growth or decay of the dependent variable is limited. In a logistic model, the population P, after time T is given by the function, P of T is equal to C over 1 plus A times e to the negative bt. P is the finite population after time. T is, of course, time. A, B, and C are constants, and A and C have to be positive, have to be greater than 0. If B is positive, then this is a growth model. If B is negative, then this is a decay model. C is called the carrying capacity. This means that as time moves on, as time increases, as time increases, the final population will equal the carrying capacity. So as time gets longer and longer and longer, we'll start getting closer and closer to that carrying capacity. Okay. Let's go ahead and work the next problem. Fruit flies, those annoying fruit flies. They're having a party in your fruit bowl at home. Suppose that the fruit fly population after T days is given by P of T equals 230 over 1 plus 56.5 times e to the negative 0.37 T. A, state the carrying capacity and the growth rate. Okay. So for A, our carrying capacity, we are not going to be able to get past 230 fruit flies. So that is our capacity. And then your growth rate is 0.37. So it's all there. Carrying capacity, growth rate. is 0.37, or our fruit flies are growing at 37%. And I believe it. Those things triple, double, triple in no time. Okay. B, determine the initial population. So to determine the initial population, this means 0 days. So for B, we have P of 0. We're going to plug in 0 for time. And you'll get 230 over 1 plus 56.5 times E to the negative 0.37 times 0. All right, let's clean this up a bit. You'll get 230 over, and this is going to become E to the 0th, where anything to the 0th is 1. So we'll just have 230 over 1 plus 56.5, or 230 over 57.5. And let's see what our initial population of fruit flies was, since we left the door open, or wherever they come from. 230 over 57.5, and we get that the initial population that flew into your house was 4. And that's all you need for them to create millions more. Okay. C, what is the population after 5 days? So this time we just plug in 5. $230 over 1 plus 56.5 times E to the 0.37 times 5. Okay, there's no simplifying this one, because now we're going to have some other type of exponent other than 0. So I'm going to type it in just like I see it. 230 over 1 plus 56.5. Oops. No, go back there. There we go. Times E to the negative 0.37 times 5. And after 5 days, these fruit flies are now a population of 23.27, but we can't have 0.27 of a fly. So it's just going to be 23 flies. Math lab may make you put 24 since you're at 0.27, but I hope not, just 23. And you technically could have 0.27 of a fruit fly. I know at UTSA, when I was on campus, I forget what class it was, but they allow students to create their own type of fruit flies. It's pretty cool. You get to create fruit flies with different color eyes, fruit flies with no legs and just wings, or no wings and just legs, maybe even half a fruit fly. So I just remember, I forget what building it was. I was just walking upstairs and there's a fridge full of fruit fly vials. So pretty crazy. All right. And D, how long will it take for the population to reach 180 fruit flies? So D, that means we take 180 and set it equal to our equation, which is 230 over 1 plus 56.5 times e to the negative 0.37 t. right. And now we have to solve for t. Okay, so what we're going to do first is multiply all of this to the left side. Get that out of the denominator. We'll have 180 times 1 plus 56.5 e to the negative 0.37t equal to 230. And then we're going to divide by 180. Just get that over there. So divide by 180, divide by 180. Okay. Which means that now we'll have 1 plus 56.5 e to the negative 0.37t equal to 230 over 180 or 23 over 18. So you'll get 23 over 18. Okay. And then we're going to subtract that 1 over there and end up with 56.5 e to the negative 0.37t equal to 23 over 18 minus 1. And then we're going to divide by 56.5, but let's go ahead and combine these two into one single fraction. All right, so I'll get 56.5 e to the negative 0.37t and 23 over 18 minus 1, which becomes 18 over 18, gives us 5 over 18. Okay, and then we'll divide by 56.5. And we get e to the negative 0.37t equal to 5 over 18 over 56.5. Okay, now let's convert from exponential to log. And here's our base of the outside set equal to the inside. So we're going to get the natural log. I'll put big parentheses here. 5 over 18 over 56.5 equal to negative 0.37t. And now divide by 0.37, and we get the natural log of 5 over 18 over 56.5 over negative 0.37 equals t. And here we go. Type it in just like I see it. Natural log of, oh man, you're gonna have a fraction here and a fraction there. 5 over 18 over 56.5 over negative 0.37. And we get 14.4 days. So after 14.4 days, you'll have 180 fruit flies. Eesh. So of course, just a bunch of moving the equation around, rewriting it, and just be careful with every step. So that is our logistic model and a graph that represents the equation. So we see we started out at, let me zoom in a little more. There we go. So we see we start out at 4 fruit flies. Then after 5 days, we're at 23 fruit flies. And then, of course, the population keeps increasing. And then after 14 days, you're at 180. And we still haven't got rid of that fruit, or we just haven't been home. And now that population has reached 230. And now maybe we've come home and started eradicating all those fruit flies. Okay. And properties of the logistic model. The domain is the set of all real numbers. The range is 0 to the carrying capacity. There are no x-intercepts. You have a y-intercept when x is 0. You have 2 horizontal asymptotes. One is at y equals 0, and one is at y equals the carrying capacity. P of t is an increasing function if b is greater than 0 and decreasing if b is less than 0. So here for our problem, b was greater than 0, which means this is an all increasing function. There is an inflection point where P of t, the final amount, equals half of the carrying capacity. So what an inflection point means is where the graph changes direction. So we see that for this graph, you are called concave up. So this is called concave up. And then you hit the inflection point, which is half of the population, which is probably at 115, since our carrying capacity is 230. And then you go from concave up and you switch to concave down. So that's what an inflection point is. It changes concavity. The graph changes direction. And then the graph is smooth and continuous. Okay. And there we go. That is 6.8. Exponential growth and decay models. So that finishes that.